This video will demonstrate how to make a kinematic model with a custom hardware using 2D layout and converting it into a set of conceptual 3D blocks. Each of those blocks can be detailed separately. Everything starts from a 2D layout, so what we're doing here, we're defining the shape of one of the blocks. This will be a main body, defining a set of parameters which will help you to control the size of each of the items. So we can define the depth, height, etc. When all the parameters have been set, we can apply some constraints if needed, and then we will define a pivot points for a hardware. It's a bit unusual, but since we are doing custom hardware, that's why we can use those pivot points as references. Now the geometry can be converted into the block. Now the next block can be generated. Using the same principle, apply constraints, set dimensions, and when all the dimensions is on the place, we can set this geometry to be a block. Okay, so now we have two blocks, so we can change their color to have a better visual appearance, and then we can apply constraints between two of the blocks. Now the third block can be generated. Again, the same story here, we define the constraints, then the parameters, and finally this set of geometry can be converted into the new block. And there will be a few custom hardware items, so we can define them. This can be set as a block. And we can apply the constraints between multiple blocks, as you may see. And in such a way, we can also design our custom hardware. I'll skip this step because it's a bit time consuming. So we have our 2D hardware layout. This allows you to easily check if the thing moves as expected. And if you see that the movement is correct, then we can do more detailed 3D objects, which in this case will be just the basic blocks, which allows you to check how the things performs in a 3D. Okay, we can give a name for the solids, add some parameters like thickness of the panels and so on. And when all those parameters have been set, some adjustments can be done. So in this case, looking from the bottom of the model, we can define a rectangle, set its offset from the side, which will be equal to the panel thickness, the same from the bottom and another side. And now let's do an extrusion, which will go to the height minus panel thickness. As you can see, even without having a panels, we have a shape which basically reminds a final model. This will allow you to check a collision detection and see if those objects actually not overlaps in the 3D. Okay, so now we can set the extrusion through all the depth in order to make some holes, which will be used like a pivot points for all this assembly. Using the same principle, next block can be extruded, and we can define names for those blocks and extrusions in order to make our changes easier. In this case, we can use a shelf feature to define the shape of this block. So once it's done, another extrusions can be made. Then we can have a separation line for the block. In this case, it will be a bottom of the bed. So we can use the constraints and the parameters to define size, as we know already. So as you may see, we are defining the general volume of those components. We're not splitting them into the details, into the subcomponents. We just want to be sure that in 3D we have a right layout. This will be completely enough for our goals. The next extrusion will be a portion with the desk. The same width as the bed block can be applied here. Set the name for solid. Again, we can make a shelf using panel thickness as a criteria. We can already see a 3D layout and see how it performs without a lot of effort. Again, some holes to have a pivot points, because maybe they will be adjusted in the future, so we want to make sure that we have some reference geometry. And now we can use our sketch, project the geometry of joining item, joining element, define its thickness, and see if the components are not overlapping in the 3D. If not, that's okay. If some overlapping is detected, we can do adjustment, define where those components must be placed. Once we have all the main blocks, new assembly can be generated. Since we are using skeleton design method, no constraints are needed in order to have the components on the right position. Okay, and once the components are on the right, correct place, we can change their behavior. So in this case, we're removing grounded status and we're applying constraints instead. So what it allows you to do, it allows you to check kinematic in a 3D. So in this case, when all the constraints will be on the place, we can use collision detection and other analysis methods allowed to be used by Inventor in order to check if our model meets our design criteria. Okay, so once the component is on the place, we can place the hardware item. In this case, there will be a detailed mechanism which can be placed on the right position using constraints. Since it's quite complicated mechanism, we must apply some constraints here and there to see if everything works in the way as we expected. This module can be set to be flexible, and it makes it possible to check kinematic. So in this case, we can enable contact solver and see if it really moves as it should. So the contact solver detects collision between the components, and if they collide, then the movement is stopped. So we see that there is nothing which stops the components from being moved in the right location. On the next step, we can add details. So in this case, we will open one of the blocks, and then a skeleton dress-up function of a Woodwork for Inventor can be used. In this case, we would like to get the same parameters as we used in our initial concept file, so therefore we just link the parameters, and then we can use them in a dress-up function. So as you can see, now we have panels. The skeleton now can be hidden, and we have multiple solids. Again, it's worth of spending some time on giving the descriptive names for the solids, since those names will be used as the name of the new files when the assembly will be generated. And once it's done, the new assembly can be generated. So visually it may look similar to what we already had, but in terms of Inventor, this is like a real assembly, and now we can apply all the operations that we can do with assembly. So in this case, we can save the file and assign the materials. This could be made of a laminated board, so we can find the right one by using filter. Now the material can be set. And once it's done, then cover materials can be applied. In this case, we will apply some edge banding on the edges. Then it's time to set the hardware. So for this purpose, we will use work planes, which will define the position of the hardware items. Once the work planes have been set, we can use them like guides to define the position of the hardware elements all across the assembly. When you need to do some changes, then we can change the position of the work plane, and the position of the corresponding hardware items will be changed too. So now let's place the hardware items from a library. Use a touch tool for doing this. And to place the hardware, it's enough to just indicate the reference geometry position. Once it's done, the hardware is on the place. Now another hardware can be placed in a similar way by just indicating a reference geometry. That's it. Now some changes can be done by modifying initial skeleton file. So as you can see, in this case, we just use a direct tool to change the position of the backplate, and that's it. It's also moved. Now the next component the desktop can be detailed using similar principle. We will link the parameters from the skeleton file using link function, choose the parameters for export, and once the parameter had been exported, we can use them in our design. So in this case, we will use a dress-up function with the panel thickness value to define where the panel should be. We will get similar object on the left and on the right, so therefore only one side will be made as a component. Okay, so here we can use a direct to adjust the position of the components. Okay, we can move solid if needed, so the desktop can be moved higher. Also, we can do some fine tuning. We can move the faces and so on. So once we found the right position, then we can use the make components to set a location of a new components. Again, they can be named in an appropriate way to make our navigation in the browser easier. And of course, those names will participate in the BM generation. Now we can use the same workflow, define the work planes, choose a hardware item, pick a reference points, and the hardware is on a place. We can use a conformat in this case because it will be not so obviously visible. So the conformat is quite robust item of the hardware, so the desktop must be fixed firmly on the place. That's why we will use it here. And again, we can define the materials, define the edge bandings, like that. We can select individual faces or we can select them all around. In this case, I prefer better control, so that's why I'm working in a single selection mode. But you can select all the edges of the component in one single click. Okay, so we opened the next component, which will be the bed. In this case, we will use the same workflow and choose the thickness of the panels, where those panels should be resided. And now some additional work planes can be used to define the position of the supports. So there we can define the size of the area which can be occupied by the supports. Should be like a wooden profiles in this case, and they will lie flat on the panel. So there's the panel which will define play like a support role and just like a joining item. Okay, and then finally we can build the front wall. Okay, and that's the object which will be used like a supporting element. Now we will define the size of a single profile, knowing the total height of a niche. Yeah. And we can define the offset from the side, the final width, which will be fixed, and the pattern will be generated knowing those two values. Okay, so one of the profiles is already generated. We can give a names for files for making navigation easier. And once all the components have been renamed, then the new components can be generated and all they will be placed in a new assembly file. There will be two identical components, so we can copy one of those and place on the other side using constraints. They will be not 100% symmetrically adjusted, so that's why constraints will be used instead of a mirror. And then the pattern can be generated. So we know the total width, of the niche, we know the width of one of the items, so that's why we can define how many of those will be placed evenly using some simple math here. Another support item on the other side of the bed can be placed using constraints. Now it's time to set the materials. We're using material groups. Some panels will be made of a laminated board. Some of those which are not visible will be made of a regular board. And of course, there will be profiles, wooden profiles, which will ensure the rigidity of our structure. If we set the material for the pattern item, it's enough to do this for a single element, and all those pattern items will be made of the same material. Now we can set the edge bendings, as we already did before. Similar principle can be applied here. And once it's done, we define the thickness and just apply the materials. Now the work plane in the middle of those supports can be generated in order to define the position of the hardware item. The usage of the work planes makes the hardware set very flexible, so you can basically deal with any situation you can face with a real scenario. There is no limitation, just add the reference geometry in the place you need, and then you can use it for your hardware positioning. So in this case, we will use a minifixes. So we will use a confirmat. Again, they will be not visible because of the mattress, which will lie on the top of all that structure. So that's why the confirmats will be used here. Now we can use a pattern for the hardware using similar workflow. And that's it. So the hardware is on a place. Now we can hide components we don't want to see at the moment, and then continue to work with the hardware. Since this component is quite complicated in terms of how it should be built, then we need to spend some time on making the hardware set in the right way. So once we have one unit on the right place, we can again use patterns, mirrors, and other productivity tools to define their position. And basically, we are repeating the same procedure again and again with another set of geometry. So this process may look a bit routine, but you can understand that there is no automation possible, because we are building some new structure. If you would have some similarly looking model already designed, then of course we can utilize it in our next design by making a copy of it, and then changing the parameters. If we need to have a wider or taller unit, it's easy to do by copying existing one with all the hardware, all the materials, and that's just changing the parameters. But in this case, what we do, we're making all that stuff from scratch. And now it's time to build the final assembly. So what we're doing, we're placing components using a new assembly file. And then once we place them, as you can see, the components are on the grounded at origin. So that's why there is no need to apply additional constraints. And so that's the final assembly. And now we can save it. Now we will place some hardware on the right position using constraints. Of course, if you'll find that this custom hardware must be used somewhere else, not only in this assembly, then you can define this like a standard hardware and apply the rules to automate its positioning, as you can see, as you saw that with the minifixes and confirmants. So the same can be applied here. Another component on the other side. And now the final object, the support mechanism. It's a bit tricky to set its position because it has a lot of adjustment points, and you want to check what of those points will be the right one. So we can set them manually. Using constraints. This can be set to be flexible in order to have an option to change the distances between the items. And this will make it behave similarly as it really behaves in the real world. So we can have like some sort of a 3D prototype without even having anything in our hands. Final adjustments of missing constraints. And once all the constraints is on a place, now we can see that the components behave as expected. So we can see it from the side, how this mechanism moves. And if some adjustments needed, you can easily do this by just changing the skeleton parameters. Okay, we can use a context solver to check collision and see where this item actually stops. And now we can do the remaining steps in order to prepare the data for manufacturing. So first we can define real material names and codes by using material replacement. So we can use a Excel file as a source of the data. Since we can use a custom-made Excel files, then the mapping may be needed. We define what columns contain a code, name, etc. And once it's done, we can utilize the data from Excel using a filter or just scrolling through the list. Then the material and appearance replacement can be done. We can see the changes. And on a single model, we can apply multiple color solutions in order to find the right one. So instead of making the changes on the material group level, we do this on the mapping schemes. Okay, so we find the right solution. Then the autoplot can be used in order to generate a set of drawings. And as you can see, there's a lot of parts in this assembly, and all they was placed on the drawing automatically with all the annotations needed for manufacturing. On the next step, we can do a CNC. So we have a specification, we have drawings and the CNC as a data for manufacturing. So we can use automated generation of CNC files. And as you can see, we get all those automatically. So basically you can see how much time it took to make a design and how much time was spent on making data for manufacturing. So on the next step, the nesting layout can be generated in a similar way using automated nesting generation. So let's see what do we have here. All the panels are divided by material in multiple work purposes, so we can see the nesting layout and do the changes if needed. That's it. So that was the demonstration how Woodwork can help you to design custom-made complicated furniture with a kinematic inside using 2D layout as a starting point. Thank you for your time, and we will see you in the next videos. Good luck.